Yeah, let's talk about sagging, especially Sommer sag. And there's the fundamental concept of Sommer knee point for bicomponent conductors. What are the bicomponent conductors? Well, it means that the conductor is made with two different types of material. So again, I'm going to use a plot here to make the point. You have temperature for the x-axis, and then you have sag for, let's say, the y-axis. If I were to draw out the sag versus temperature, and if I do it for ACSR, it would be like that. And the slope here, by the way, you could say this is really directly proportional to the, CTE of aluminum. And the reason for that is the aluminum dominates Sommer expansion when the temperature is below the Sommer knee point. And what is Sommer knee point? Sommer knee point is a temperature that at which the aluminum reaches zero tension. So they were under high tensions, and then with temperature going up, the aluminum expands faster. So gradually and eventually it's going to reach a point where the tension in the aluminum strand becomes zero. And then if the temperature further goes up, the aluminum strand may go into compression. And when the aluminum strand goes to compression, it's the core material that takes over, and the sag will be driven by the thermal expansion in the core. So if I were to do ACSR, and ACSR in terms of the aluminum dominating the sag, that would be how it's going to be. And there is a point that for ACSR that you will have, let's say, I'll put a slope here. And there is a knee point here, even for ACSR, and typically this temperature could be pretty high. Let's say, it's about 120, let's say 125 degrees, okay? That's how ACSR behave, because ACSR is also a bicomponent conductor. There's a knee point. And the way the ACSR is put together, you do have steel, and you do have the aluminum, and the knee point does change with respect to what is the tension in the conductor, because ultimately it is for transitioning the aluminum strand from tension to compression, okay? So it is not a fixed parameter. It is dependent on what is the tension load, and also what is the configuration in the conductor, how much is aluminum, how much is in steel, so how much the aluminum is taking on tensions. So now if I were to look at ACSS, keep in mind the ACSS, you have annealed aluminum, so they take less tension, and when you take less tensions, your knee point is going to be less because you don't have to rise in temperature as much to achieve that transition, right? So let's say we have ACSS here, and the slope, by the way, is very similar. In the early portions, it is still dominated by the aluminum. So this temperature could be, 70s, 80 degrees, and it's very similar to some of the other advanced conductors. If I were to draw out the ACCR, which is another high temperature conductor, and they use aluminum alloy, by the way, and their Sommer knee point is going to be a lot higher because keep in mind the composite core that they have does not have as good of a strength. So the aluminum strands is taking high tensions. It's going to require more temperature rise to get to that point. So their Sommer knee point might be higher and maybe lower than ACSR, but maybe higher. So it will be somewhere here or here, but it's definitely higher than ACSS, right? In their slope, it's going to be a little bit less. than the ACSR, the steel slope. Why? Because we have composite in that conductor configuration. So they have, relatively speaking, lower sag, right? And I probably didn't draw this in a fair way for ACSS, so let me redraw that, because ACSS does have, I should draw this out very, it's going to extend beyond this table here, because the temperature here, we're looking at much higher temperatures. And ACSR, by the way, they normally don't go above the knee point, so we normally don't even see the summer knee point. So you have ACSS that goes to high temperatures, and then you have ACCR, which would have a shallower loop. So they cross because the slope here is a little bit more, less compared to the steel slope. Okay, and if I were to put ACCC versus TS here, I think our summer knee point is going to be similar here to ACSS because it's a near aluminum. And what's going to happen is with TS, you have a straight line. Because there's virtually no thermal expansion from the composite core. And ACCC is likely going to be similar, but with a slightly higher slope because they have glass fiber in it, and they will have a little bit more thermal expansion. We did talk about some of the other conductors, including, for example, gap conductor. And by the way, the gap conductor, if you look at the knee point being much lower, because the way they do it is, in the installation phase, they only tension the steel. And then a couple of days later, when the aluminum is all relaxed, they fix the aluminum. So the aluminum has zero tension at the installation temperature. So their knee point is actually the installation temperature. After the knee point, they will follow the steel slope. So they will go up like that. So they will have a pretty high sag at the very high temperatures, but it's less than ACSS, simply because they have a lower knee point. And when you look at INVARs, okay, the INVAR has a very high knee point because they had to use high temperature aluminum alloy. And even though their knee point is high, their thermal expansion is going to be a little bit less. So the slope is a little bit shallow. So ultimately, they will have lower sag compared to ACSS. But it does have that relatively high thermal knee point because there's much greater tension in the aluminum strand in the INVARs. That pretty much captures the sag tension behavior and the thermal knee point related to conductors.